So today we're going to talk about Infineon's CoolSiC technology. This is silicon carbide MOSFETs, both a regular MOSFET technology as well as diodes in a variety of different packages, which you can see down here. And we'll talk about some of the advantages of CoolSiC technology in terms of the core technology itself. We'll talk about the gate oxide structure and how that plays into the long-term reliability of the devices. We'll comment on about a few of the investments that Infineon is doing for CoolSiC technology. I'll give you a couple of examples about harnessing the performance of silicon carbide in some particular applications. And then I'll also give you an overview of the Infineon CoolSiC portfolio, and then touch on a couple gate drivers that match up very nicely to our product portfolio. So Infineon has a long history of silicon carbide devices. We first started developing silicon carbide in 1992. And as you progress through this timeline, what you'll see is that, we were the first to really release silicon carbide diodes into the marketplace. In 2015, we were the first to start working with 150 millimeter wafer sizes for silicon carbide, which really helped, expand economies of scale of silicon carbide, transitioning from smaller wafers like 2-inch and 3-inch up to their 6-inch wafers at this point in time. And then, of course, in the recent years, we released our portfolio of CoolSiC MOSFETs. And you can also see here that we explored some other technologies like JFET technology. But most importantly, Infineon kind of skipped a critical step in terms of the development of silicon carbide devices and did not develop DMOS-based devices and focused primarily on trench-based devices. And trench-based devices, have a long history with Infineon with our silicon-based device technology utilized in MOSFETs, silicon MOSFETs, as well as silicon IGBTs. And this allowed us to utilize these decades of experience in that technology to really release a product into the marketplace for silicon carbide that was far better than a lot of the other technologies that existed at the same time period. So looking at the broad portfolio of Infineon, one of the advantages for Infineon is that we're agnostic in terms of technology. We have the largest portfolio of silicon devices, we have a complete portfolio of GaN devices, and of course, the silicon carbide portfolio that we'll discuss today. So when we engage with customers, we can really analyze the application requirements and then recommend the correct technology for your application. And it could be, in a given application, IGBT technology is beneficial, or, you could be considering silicon carbide for an application, but it might work out that a regular silicon MOSFET could be ideal for your application. And we can help guide you through that process. And I think that's one of the most important things to consider is that we have all the technologies. We're the market leader in power semiconductors globally, and we can help you. So one of the things I wanted to talk about when we talk about reliability of silicon carbide devices is really the gate oxide structure. And here you see this yellow line box that follows around the gate oxide structure. And this is a critical area in terms of the long-term reliability of devices. And this particular structure here of the cell of a silicon carbide MOSFET represents a DMOS-based device. And what I'll touch on here is really the challenges in terms of reliability, in terms of time-dependent dielectric breakdown, and how extrinsic defects in the device material or base material, silicon carbide boule or wafers, can cause some challenges in terms of making sure that you're creating a reliable device, and then how Infineon is basically ensuring that we're releasing, product which has the highest reliability, longest lifetime into the marketplace. So when you look at the raw base material of silicon carbide, what you see here is that silicon carbide has a very high defect rate in terms of its core base material. So you'll see particle inclusions, porous gate oxide, and in this X direction here, you'll see a number of defects in terms of fissures or chips or something in the structure. And this becomes very critical in terms of the development of a gate oxide in a device and ensuring that you're filtering out any devices that could be potentially affected by some of these extrinsic defects. So let's compare a little bit about the different structures of silicon carbide MOSFETs that are in the marketplace. So on the left side here, you see a DMOS device, and on your right side here, you see a trench-based device that Infineon is developing. And one of the things you notice here is this 70 nanometer gate oxide thickness. And this gate oxide thickness is standard of what you typically see in the marketplace for both an IGBT-based device or a silicon MOSFET. And this has a known reliability in terms of dielectric breakdown of the device, and proven to have a very long lifetime in the application environment. The reality is that when comparing the trench base to the DMOS device, if you were to have the same gate oxide thickness, is that the overall size of the die for a DMOS device would need to be substantially larger in surface area in order to have the same RDS(on) specification for the same gate oxide thickness. And the challenge here is that that's not really happening in the industry. So in order to have devices that have the relatively same area of die size and can be competitive, in the mass market, you have to reduce the overall gate oxide thickness of DMOS devices into the range of 30 to 50 nanometers in order to have a competitive die size and be competitive in the marketplace. There are challenges, however, of having a lower gate oxide thickness, and this particularly comes into dielectric breakdown of the device and creating extremely high field strength on the device, which can lead to premature failure. And we'll see as we transition through the slide, particularly the impact that has with respect to extrinsic defects and being able to filter those out in the manufacturing process. So just going back here to the structure, what we see here is a Y-bolt curve, and along the x-axis you have your time to failure, and on the y-axis you have the rate of failure. So the further you move to the right of this curve, the longer lifetime and reliability you have of a product, until the point where you reach this intrinsic branch. And the intrinsic branch is basically the wear out of the device. This could be 50 years, 25 million or cycles or something to that nature, where it basically is a limitation of the material itself. So most of the time you're operating in the extrinsic branch here. And what I'd like to show you as we progress through the slide is the challenges that silicon carbide bring in terms of these extrinsic defects. So on slide 7, or previously, we had shown you about all those little defects, porous gate oxide structure or particle inclusions that happen. And there's a key differentiation between silicon carbide and silicon. Silicon, has been in the industry for 30 years, and there's a substantial difference in terms of the ppm rate or quality of the boule or base material that you have with silicon versus silicon carbide. There's almost a 4x order of magnitude less inclusion rate in silicon MOSFET or silicon material versus silicon carbide. So it becomes very important to develop a process where you can filter out these extrinsic defects that exist in the raw base material. And Infineon has a particular answer for this for you, which we'll cover in the coming slides. So just a difference in ppm rate, you're talking from 1 to 10 ppm rate. And silicon carbide will get better over time, and the amount of defects that are in the product will reduce, but it will take some time. You're looking 5-6 years before you really see a closer parity in terms of the reliability of or the quality of the base material. So when we talk about those defects that are in extrinsic defects that are in the base material, one of the things that becomes clear to you is in the construction of the devices. So I showed before that there's a high number of defects that happen in the X-plane of a silicon carbide wafer material. And when you look at a DMOS-based device or a planar device, what you see is that the gate structure is really happening across this X-axis. So here you can see the P regions that are a critical area for dimension. So with the way that you construct a planar device, you tend to have the potential for a high number of defect density or issues in the area which is critical for the performance of the device, and that's this P region here. And when you talk about current flow inside of a DMOS device, you basically have a device that goes from the source area and then transitions down vertically. So you have this area where it becomes a critical dimension here in the x-axis for the construction of the device. And because of the number of defects that you have in the x-plane of silicon carbide, or the horizontal plane, you create an area where you have to have a relatively large structure in terms of a cell for a planar device in order to ensure the same RDS(on) specification. So just take, for example, these two devices that we show here, the trench gate or trench cell and the DMOS cell, you can see that there's a clear difference in the size of those devices. And that's because of this particular P region and having to have enough surface area in that region in order to assure a proper defect density. Now, conversely, with the trench-based device, you have all of your P region that happens in the Y direction, and so a vertical direction on your screen. And the processing equipment and defect ratio of silicon carbide in the Y direction is significantly lower, so that allows you to have a much smaller overall cell structure for a trench-based silicon carbide MOSFET. And that allows you to have smaller die sizes, better economies of manufacturing, higher yield rates as well, because these defects can happen anywhere in the map of the silicon carbide wafer. And so if you have a smaller cell structure, that means that you have less devices that are affected. So overall, your yield will be higher with silicon carbide trench-based devices. The other critical characteristic here is this field strength. So this 3 millivolts per centimeter, this is basically the overall field strength that happens on the device. And this plays a critical characteristic in being able enough to, one, show reliability of the device, but then two, also filter out defects that happen in the device. And we'll get to that. So just taking a look at this YBO curve again. So one of the ways that you can improve the reliability, so again, the x-axis here is the time to failure, and the y-axis here is the rate of failure. So if you drive the gate harder, increase the voltage on the device, so for instance the burn-in voltage, you begin to move further to the intrinsic branch curve here. So the higher you drive the gate, let's say instead of driving at 15 volts to validate a device, you then drive it or hit it with 30 volts. And so that pushes you further down in terms of the rates of failure, and further to the right in terms of the reliability or long-term rate of failure of the device. So one of the things that Infineon is doing is basically driving our gates during a screening process. So we screen 100% of our devices once they are packaged at high gate drive voltages to eliminate basically all of these extrinsic defects. We filter those out through testing 100%. And that allows us to offer a product that's extremely reliable and does not have these defects which cause early failure in the application. And one of the capabilities that allows us to do this is the gate oxide structure of our device. And so, as you have a certain gate oxide field, and typically this is in the range of, let's say, 10 millivolts or 12 millivolts, you start to reach this dielectric breakdown of the device, where basically then the device fails. And if you have a higher gate oxide structure, you can see that the dielectric field on the device is much lower than compared to planar devices that have a lower gate oxide structure. Just in comparison, the gate oxide structure here for IGBTs and MOSFETs is in the range of 80 nanometers. Our silicon carbide devices here are in the range of 70 nanometers, and then you're looking at planar devices. Some of those get as low as, let's say 35 nanometers in terms of gate oxide thickness. And you can see on the right here is that once those devices are driven at the recommended gate drive voltage, the dielectric field on those devices are quite high. And so this prevents these devices from being driven hard, in terms of being able to filter out the dielectric or the extrinsic defects in the device. So here again, when we talk about this curve, the higher the voltage you drive onto the gate of the device, the further to the right that you move on this curve. So a more reliable product with less defects overall, or less, failure, a lower failure rate. And so the gate oxide thickness essentially has an exponential improvement in terms of the long-term reliability of the device, while only providing a small linear reduction in terms of the RDS(on) per chip area of the device with respect to gate oxide thickness. And there is a test that we've done in a study that Ohio State has done as well, where you can compare the long-term robustness of the gate oxide structure and therefore the long-term reliability of devices in a particular test. So what you do, and marketing people like to talk about little dots on the screen here as an example, but as you look at this chart on the right, you can see my cursor, you're seeing basically the gate being hit with different voltages. So they're starting at 20 volts, then increasing to 30 volts and 40 volts. And when you see this fall in the line, as an example here with this DMOS-based device, this is when it reaches its dielectric breakdown and the device fails. And you can see here this red-orange color. This is the Infineon devices. And what this shows is that we have a significantly higher or more robust gate oxide structure, and allows the device to be driven up to higher voltages before you start to reach this dielectric breakdown at almost 50 volts. And when you compare that to the long-term reliability of the devices, what you see here is that Infineon devices generally have essentially an order of magnitude higher reliability than some other devices on the marketplace. And this is primarily driven by the thickness of our gate oxide structure and the trench-based topology that we have of our devices. So this is just a comparison between devices. You can do this in your own lab and compare other devices. We do have a white paper on our website about this, and of course you can also look up the Ohio State paper that's been done on this as well. So Infineon is now in our essentially generation 1.5 devices, what we call our M1H, our first series of devices, which was from a discrete perspective listed as the M1 series. That was a 45 milliohm device. But then very quickly we released the M1H series. And what we were able to do is improve the cell structure of the silicon carbide MOSFET and get about a 12% better RDS(on) specification based on chip size. We also widened the gate source voltage range and basically allowing you to have a 15 volt or 18 volt specification with a maximum VGS specification for transients up to 23 volts. And we'll touch a little bit on more on the benefits of this, particularly with respect to RDS(on) and or short circuit capability in a future slide. We've also increased the maximum junction temperature, so we have overload capability for 175C. And then we added a number of new chip sizes that are available both in discrete product offering from, let's say, 220 milliohms all the way up down to 7 milliohms for discretes. And then these same dies are used in different combinations within our module product offering. And then the biggest advantage here is we've improved the long-term stability of silicon carbide. So silicon carbide has historically always had a condition where the more negative you drive the gate, so let's go say -5 or -10 volts, the higher in shift in RDS(on) specification that you would have in the device over its lifetime. And we've been able enough to prove now with the M1H technology that we can guarantee a less than 3% shift in RDS(on) specification at 175 degrees C over a 20-year lifetime of the product. So the Infineon devices are very stable. This will allow you to also select a higher RDS(on) specification in the devices, which means a lower price for you to ensure the and still have the long-term stability of the device with respect to RDS(on) in your application. So let's say that you needed 40 milliohms in your device, but you are in your application in order to keep the losses at an attractive level for you, where you could choose, a 35 milliohm device instead of choosing a competitive 30 milliohm device, and basically stay within the RDS(on) specification over the lifetime of your application. So ensuring that devices do not wear and go outside the specification and cause thermal issues in your application. So when we talk about some of the investments that Infineon is doing, we've been investing heavily. We invested in a new facility in our VLOC location. This was a $3 billion investment that we did for a 300 millimeter fab, and that's primarily focused on silicon technology. But this also opened up additional, capabilities in terms of our manufacture of silicon carbide. And then in 2021, 2022, we also announced an investment of another 2.4 billion euros in a new facility in our Kulim location. So just highlighting here, I'll show you, this is our facility in Villach, Austria. And what you have here is a 300 millimeter fab that's came online in 2021, groundbreaking in 2019. And this is our second 300 millimeter fab for power semiconductor production. Our first fab that we had in 300 millimeter production is in our Dresden location. And then we also added a new R&D building for chip development. And what I'd like to show you here is some of the technologies that we have and how they've moved and transitioned in order to free up manufacturing capacity for silicon carbide devices. So let's take a look at 2018, what you see here is that we only had IGBT6 on 300 millimeter production. We had a very high number of devices that were on our 200 millimeter production in our VLOC fab, and then of course a number of device technologies that were on 2018 on 150 millimeter production in VLOC. And you're looking at 2022 now on this top line, and what you see here is that all of the chip technologies have moved out of the 150 millimeter fab, and pretty much all of the technologies have transitioned out of the 200 millimeter. So looking to the future, we have capabilities and equipment and fabs in place to manufacture silicon carbide both on 150 and 200 millimeter equipment, and dedicated manufacturing sites at our VLOC facility, and then also coming online in 2025 will be our new Kulim facility. So we announced in 2021 that we're investing over 2 billion euros on another wide bandgap manufacturing site. This is in our Kulim facility, and here we'll focus on epitaxy processes for wide bandgap materials. This is both going to support silicon carbide as well as GaN-based technology. So here you see, we're really focusing on trying to create as much capacity for silicon carbide in the marketplace, and this is primarily driven by demand. We're seeing a number of mega trends that are driven by infrastructure investments in the Americas. For instance, the war in Ukraine driving, energy and fuel prices very high in Europe, and requiring basically, semiconductors for alternative energies, as well as the transition in major home appliances to more efficient appliances. And so because of these mega trends, and that's not even mentioning the automotive marketplace and EV charging infrastructure that's coming into place, we see very rapid growth in terms of demand of silicon carbide, and we're preparing for the future. And just highlighting here the facilities here. So we'll have a dedicated 150 and 200 millimeter production line for silicon carbide in Austria, and then the new facility coming online in 2025 for Malaysia, and sharing manufacturing. So this site in Malaysia alone, if it's just based on 150 millimeter, can generate about $2 billion worth of revenue of silicon carbide. And if you increase that to 200 millimeters, which is the plan from the very beginning, you're looking at, in excess of $2 billion. As an example in an application here, one of the things you can see here is a comparison between IGBT technology and silicon carbide technology. So in this particular example, the IM503, this is an IPM three-phase inverter topology for motor drive applications using IGBT technology. And the IM503 is a device here in the same package, but using silicon carbide MOSFETs. And this could be in the range of 40 milliohms or maybe even 35 milliohms. And this is comparing the losses of these devices. So you see the IM503 and then the IM535 here and here. And what you see at a 20 amp peak current rating is that your losses are in the range of, for instance, 49 watts for a silicon carbide device, or 70 watts for a IGBT-based device. And one comment here too is this is based on the 15 volt VGS specification. And if you were to increase this to 18 volts, you would see a substantial improvement in the RDS-on specification of silicon carbide devices, about a 25% improvement. So your losses, particularly from the conduction loss perspective, would go down by about 25%, and your losses would be in the range of, in the upper mid 35 range. And then also the same calculation here done for a 30 amp peak current. But one of the things that you can compare here is particularly switching frequency. So let's take, for example, a heat pump application for major home appliances. And you typically would operate this motor drive at 6 kilohertz. Well, one of the things that we're seeing in the industry is that the market is looking to increase the switching frequency of these compressor drives to reduce the audible noise that you're hearing in the application, as well as reduce the current ripple on the motor and improve the overall lifetime of the motor. And here you can see that there's essentially no penalty by going with silicon carbide by switching the frequency from 6 kilohertz to 20 kilohertz in the design. So you can essentially implement a 20 kilohertz switching frequency without having to change your thermal mitigation solution in your compressor drive. And so that's a major advantage for silicon carbide. What's also not highlighted here, but represented in this curve, is light load efficiency with silicon carbide devices. So particularly when you're operating a compressor drive, let's say at 30 to 40% of its peak operational power, you see a massive increase in the efficiency of the drive because of the light load handling capability of silicon carbide. So IGBT-based devices have a consistent forward voltage drop, your VCE-SAT, whereas for silicon carbide devices, it's a MOSFET-based structure. Here you have the current is the RDS-on specification and current determine your forward voltage drop. So the lower your current, because it's a squared function, the lower your forward voltage drop of the device. And just taking, for example, here, you can see that also when you're talking about peak power for silicon carbide, there's also an advantage, in terms of efficiency gain, roughly 40 to 50%. But light load efficiency is the main advantage here for silicon carbide. Here's another device that's in the works. It's a small PQFM package. It's a half bridge device with an integrated gate driver. It's in a 7x7mm package. And here's another example of light load efficiency. So this dotted line here is showing the efficiency gain over silicon carbide devices. Over IGBT-based devices. The gray line here is a low-power discrete IGBT, and this line here is a MOSFET, a silicon carbide MOSFET device, and then of course the dotted line is your efficiency gain. So you see this hump that happens at the low power range, 20 to let's say 40% of the operational peak power handling capability of the device, and then you see an overall gain of around 55% when you're talking about the high efficiency of the device. So this is a device that will be coming out into the market in early 2023, designed for applications generally 300 watts and below. For a three-phase motor inverter topology, you'd use 3 of these. For a DC to DC converter, you could use 2 of these devices, creating a device that's extremely small and compact for an application. So let's highlight a little bit more about the product offering from Infineon. So as you can see across the bottom here, we transition from low power applications to high power applications, moving from discrete-based devices to packaged devices. You have the Cyclos Maxi and Mini product offering here, which are IPMs. We won't really cover these during the presentation, but we have these available in silicon carbide, as I highlighted in that previous application examples. But today we'll focus on the discretes and then the easy module product offering in the discussion. And then, of course, if you're working on high power applications, we do have the 62mm and XHP 2 devices with silicon carbide devices. And then a complete portfolio of automotive qualified devices available as well for onboard charging and or traction drives. But those will be outside of the scope of this discussion today. So looking at our discrete product offering, we have a very nice lineup here. We have the widest portfolio of RDS-on specifications for 1200 volts. And you're looking at here devices as low as 7 milliohms and as high as 350 milliohms. And what you see here is the rollout of the next generation devices located here in the blue or blue-green color. And these devices that are shown here in the blue-green color actually feature our .xt technology, and I'll cover that in a future slide. And then we're also working on a number of new devices, particularly in different packages, like the QD pack for topside cooling or this half-bridge device. These are products that are looking at coming out either in late 2023 or sometime in 2024. The half-bridge device is pretty unique in the fact that you'd have a half-bridge topology inside of the device where you'd have either 2 MOSFETs, or you could have a boost diode, a boost topology configuration where you have a silicon carbide MOSFET and a silicon carbide diode, or just a half-bridge rectifier module where you'd have 2 silicon carbide diodes in the package. And so this will provide you flexibility in applications for higher power density. Also, we have a complete product offering of the TO263-7 devices, which aren't shown here, but they're in the same RDS-on specifications that you see here for the TO247 devices. So when we talk about .xt technology, this is a new die attachment process that we've had available in some of our modules for a while, but now we're rolling that out to our discrete product offering. And this is particularly interesting when you start to look at the low RDS-on specifications that the market is asking for. So for instance, the 7 milliohm device that we have in our product portfolio. And what .xt does is it reduces the connection thickness between a soft solder connection. So your standard TO247 devices in the market use a soft solder connection here. It's a rather thick connection layer, as you can see here on the left. And this creates a mismatch in terms of the thermal coefficients of expansion of the devices and can lead to delamination if you had a high delta T application environment. But by using .xt technology, we're actually using some type of sintering process, which creates actually a molecular bond between your chip material and your substrate or your lead frame material. And the thickness here is 1/5 the thickness of you typically see in that soft solder assembly. So what you get is about a 25% reduction in the R theta of the device, as well as a 45% reduction in Z theta in the application. So really providing a device that provides you the best performance and the best thermal cycling capability. And particularly exciting too when you talk about how much smaller the die sizes of silicon carbide are versus that of IGBTs or silicon MOSFETs. This provides a big advantage for the customer in terms of performance in the application and keeping the junction temperatures lower so that you can drive more power density in your application. I mentioned before about the differences between the M1 and M1H series. And one of the key advantages in the M1H series is that we've implemented the wider VGS specification for the devices. So you can drive the devices at 15 volts and get around 3 microseconds of short circuit capability, or you can increase the VGS specification to 18 volts, lower your RDS on specification by between 20 and 25%, but then in the same time eliminate your short circuit capability of the device. So if you're choosing a motor drive application, let's say you would drive it at 15 volts, but if you're developing a DC to DC converter where efficiency is your main driver, then you would drive the device at 18 volts. And the nice thing is here we provide you the option in a single product for you to decide how you want to drive the device to optimize for performance for your application and the needs of your application. We do have available 4-pin devices, and as well as our TO263-7 devices have a Kelvin emitter pin, just like the 4-pin device here shown. And this helps reduce your E on by about 40% and your E off by about 10%. So if your application is driving the MOSFET at switching frequencies above 100 kilohertz, then we recommend the 4-pin in your application, and it will help you save overall losses in the application. And if you're very concerned about power density in your application and overall heat, you can also choose the 4-pin even at lower switching frequencies. But obviously there is some price adder for a 4-pin device over a 3-pin device. One other thing to mention too is that Infineon generally does not need a negative gate drive voltage. We have a very high VGS threshold on our devices. So it's typically around the 4-volt range. And so in your application, there's not a big need to drive our devices negative unless you're switching at very high frequencies, above 100, 150 kilohertz, then it does provide a benefit. And as I showed before, we have a very stable device and very low drift in our devices with negative gate drive voltage. So we are capable of taking negative gate drive voltages. We just generally don't recommend them for applications below 100 kilohertz because it's not needed. We also have a high creepage package of the TO263-7 with 1700 volt silicon carbide devices internal. And these are really targeted at aux power supply applications. We've had great success with this product, particularly targeting half bridge topology, flyback converters with this quasi-resonant topology. Reduces your overall component count and really provides excellent performance. And you can see we have 3 different RDS on specifications, which provide you flexibility in your application for different power ranges. So very robust, reliable product. This reference design here is available upon request. So I previously was talking primarily about 1200 volt devices. We also have a good portfolio of 650 volt devices here. So you can see the current portfolio released in black. The toll package is now available for sampling, and then we also have similar package to what the industrial product offering at 1200 volt is offering in terms of a new product roadmap in topside cooled devices. So both QD pack and toll package, and then of course this ultra small toll package. We have a full portfolio of silicon carbide diodes available, and some of these are now also featuring the .xt technology, particularly in the latest generation targeting higher power handling capability devices. And then we have the same portfolio. This is the .xt versions that we show here. And then we also have a portfolio of 650 volt silicon carbide diodes. So again, we have a very large portfolio of devices, ideal for a number of applications. So when you're looking to increase the power in an application or go to more complex topologies, the module, particularly the Easy series of modules, makes a lot of sense. And one of the main advantages of the Easy series is that it has very low transconductance compared to other module topologies. And here's an example of the portfolio that we have. So one of the things that you might see on our website is that the M1 versions of these devices are now listed as discontinued. And that's because we're rolling out the new generation of chip technology into that same package. So the M1H versions are the next generation, featuring our generation 1.5 chip technology, where you have this adjustable VGS specification, and also the improved stability of the device and a wider variety of chip sizes, as we covered before. So this is a chart that provides you the crossover. So basically the 45 milliohm device in the past is now a 33 milliohm device, because the RDS(on) specification is specified at 18 volts, at least in the specification. That's why you see the shift in the RDS(on) specification. But these are all, as they go from left to right, the same pin configuration in the device, so they are drop-in replacements to each other. So focus on the M1H versions of these devices. These will be all fully rolled out by the end of this calendar year, end of 2022, and we'll look at discontinuing the M1Hs at a similar time period at the end of this calendar year. So if you do have some requirements for the M1 versions, now is the time to place a last time buy for these devices, but just keep in mind we have a pin-to-pin compatible device which will be drop-in replacement for you in your application, just offering you better performance and improved reliability. As an example of some of the capabilities within our team, we have the ability, because of our broad portfolio of both silicon and silicon carbide devices, to offer modules that are somewhat of a hybrid. So in this particular example, it's an NPC2 topology. And what you see here is a combination of silicon diodes, a low VCE SAT IGBT, and then, of course, silicon carbide MOSFETs. And for instance, in this particular topology, generally the IGBTs are switched at very low frequency, typically line frequency, 50 or 60 kilohertz. But then, and so you have focusing on a device that has very low conduction losses, whereas the MOSFETs here in this particular example, you can switch those at 42 kilohertz, and therefore, utilizing the advantage of silicon carbide to eliminate switching losses in your application. So you have a topology here and a module that's focused at creating a solution that's, in excess of 99% efficient in providing you bidirectional capability for applications. And we're seeing a growing need for this in solar applications as well as the EV charging marketplace. Major advantage for the Easy module product offering is that it has a lot of flexibility. This is a product that we're producing in very high volume, excess of 50 million pieces sold. And we can create custom versions of this product. So we have a portfolio of approved die technologies, and through our short flow process, you can incorporate any type of those die technologies in different topologies and create a custom solution for your application that meets your needs. This is a base plate-less design, so basically it has very low R theta performance, and it really provides you a lot of flexibility. So we can, because of this short flow process, we can have different pin configurations, and all of these packages are scalable in terms of size. So the Easy 1B and Easy 2B being twice the size of Easy 1B, Easy 3 being twice the size of Easy 2B, and now we've also released a variation called the Easy 4B, which is significantly larger, 4 times the size of the Easy 2B. And just showing you here the dimensions in general of the Easy 1, 2, and 3B product offering. If you're interested in the Easy 4B for a higher powered application approaching 100 kilowatts or higher, we can show you details on our website about the Easy 4B. Just looking at one of the devices that we've created here, it's a half bridge module with 2 milliohm RDS(on) specification. The biggest thing here is that the stray inductance of this device is in the range of 5 nanohenries, which is very small compared to other modules with different terminal connection means. For instance, the Econo Dual is closer to 20 or 23 nanohenries. So the EZ3B really provides an excellent platform for the utilization of silicon carbide in applications. And of course, by having a larger package, we're able to parallel more dies to create lower RDS(on) specifications. So just stay tuned for other solutions that exist in the EZ3B, EZ4B products if you're interested in working on a high power application. The other thing that we have is to go along with our silicon carbide devices, a very broad portfolio of gate driver technologies. And in this particular presentation, we'll focus on the right on the coreless transformer-based devices, as these have higher blocking voltages and are catered to the 1200 volt application. Some of these have a galvanic isolation and functional isolation levels above 2300 volts. We also have silicon on insulator and junction isolated devices. These are targeted more at the 650 volt range, although silicon on insulator does have some devices that are in the 1200 volt range, but they do not feature galvanic isolation or any UL or VDE qualifications for isolation. And then, of course, your low side drivers. Looking at the portfolio of devices for coreless transformer technology, what you see here is a couple different categories of devices. So you have high creepage devices with 300 mil spacing, and then you have our compact devices with 150 mil spacing. And these devices have different qualifications in terms of isolation levels that I'll showcase on the next slide. But there's a variety of devices that exist in a variety of different power gate or output power ratings. So you can drive some pretty low RDS(on) MOSFETs, even the 2 milliohms, with some of these high output capability devices. This shows the isolation levels and the qualifications. So we do have devices that have VDE class 11 qualification. And the latest series that we've added to the product portfolio is this F3 Enhanced product offering. It's a compact device, very cost competitive, and provides high levels of isolation and excellent performance. So consider these for your next design. Any of these products are suitable to be utilized with our silicon carbide devices and optimized for the gate drive voltages that we typically have in our devices, that 15 to 18 volts. Some of these have Miller clamp capabilities, so you can drive these devices negative. So just to summarize the presentation today, we have a very wide product offering of silicon carbide devices, both in 650 volt, 1200 volts. We're also developing some higher voltage devices, a portfolio of 2000 volts and higher devices, even in discretes for those voltage ranges. So if you're working on a converter that's looking at 1500 volt bus, we'll have a solution for you at the beginning of next year that's available. We can even sample of that now. But these devices have a wide and flexible gate drive voltage, so you can drive it at 15 volts, get short circuit capability, or drive it at 18 volts and have a lower RDS(on) specification. We've released the M1H series of technology, or generation 1.5. This increases the maximum gate voltage up to 723 volts for transient voltage, so providing you more margin for noise in your application. We also have short circuit capability at 15 volts. The device has been optimized for 0 volt turn off, so you don't generally need to drive our devices with negative gate drive voltages. And then, of course, the increased reliability. We talked about the gate oxide robustness, but then also the long-term stability of these devices because of the changes we've made to them. We have the largest portfolio of silicon carbide devices in the marketplace, ranging from 650 volts all the way up to 2000 volts and higher. So you can contact us about those. And then, of course, we have the complete portfolio of gate drivers to match with our devices, both discrete-based and modules. So, Chris, that's it for me. I hope everyone enjoyed the presentation and found that useful.